Hello, this is part 2 of the section about difference equation basics. Now in the first video, we learned about the idea that a difference equation is modeling change. In other words, change is just the future minus the present. And so if we have a variable that represents the current amount, then what we're really looking for is a formula or a function that will describe how that amount is changing. And don't forget, you always need an initial value to complete the model. So we did a simple example last time with a constant change, and now we want to go to another level of difficulty because most financial situations are going to be more complicated. So let's jump into a second example here. Suppose I have a CD, a certificate of deposit, and I want to invest $5,000 in it for, say, maybe 5 years. My interest rate annually is 5%, and this CD compounds quarterly. Can I come up with a formula that describes how much is in the CD after each quarter? So what we're going to do is we're going to let A sub n equal the value of the CD after n quarters. And it's best to use a time period that matches how often it's compounded. Now, we're investing $5,000, so that immediately tells us that A sub naught is 5,000. And because there's 4 quarters in a year, then since my interest rate is 5% annually, then my interest rate per quarter is going to be that 5% divided by the number of quarters in a year. And of course, that works out to 0.0125. And so what we would like to do is find the formula then for A sub n. And since we're going to use a difference equation, let's start with delta A sub n. And if you know how compound interest works, basically what the bank is going to give us is a proportion of however much we have invested. And that proportion is based on this quarterly interest rate. And so basically we're just going to take the R times the current value of the CD. So this delta A sub n basically represents the interest. In other words, how much is my value of my CD going up? It's however much interest I'm getting. And since that's proportional to the amount of the CD already in the bank, then that's my formula. So in other words, this is 0.0125 A sub n. Or to write it another way, A sub n plus 1 minus A sub n is equal to 0.0125 A sub n. And if I solve for A sub n plus 1, notice that's bringing in A sub n, so there's one of those plus another 0.0125. So that's going to be 1.0125 A sub n. And don't forget my A naught is 5,000. And so this is our discrete dynamical model of the situation. Remember, this is a recursive relationship. So if I want to know what A sub 1 is, all I have to do is just multiply 5,000 times that number and I'm done. If I want to know what A sub 100 is, I'm going to have to do that 99 more times. And if I want to know what the value is after 5 years, then I need to find A sub 20. Because 5 years worth of quarters would be 20 quarters. Now, we could punch that in our calculator 20 times. We could use a spreadsheet, or we could find an explicit formula. An explicit formula is not bad because this is just a multiplicative relationship. And so if you think about it, every time I do the iteration, I'm just multiplying by 1.0125 again. And so my explicit formula then would be A sub n is 1.0125 to the nth power times A sub naught. And now we can plug in 20 for n more easily and get the same answer as if we would have done it the other way. So in either case, we're going to get approximately $6,410. So in other words, we earn more than $1,400 worth of interest in 5 years on the CD because we got 5%. Let's take an even more sophisticated example. So in this example, we're going to assume that we have a savings account still. Now we only start with $1,000, a lower interest rate, so only 3%, but now we're investing another $100 every month. okay? And this account is compounded monthly. So once again, we're going to let A sub n equal the value of the savings account after n months. And remember, we said we're starting with $1,000, so A naught is $1,000. In this case, our interest rate is only 3%, but I'm dividing that by 12 because there's 12 months in a year. And so that works out to 0.0025 for a monthly interest rate. And then we also have one more thing to keep in mind. We'll just call it D. A monthly deposit is $100. And so now the question is, how do we model our delta A sub n, our change, in this scenario? Well, compound interest hasn't changed, right? The relationship R times A sub n, that's the same as before. The A may change, the R may change, but the relationship is the same. What's different is we're adding a constant amount each month. So in our case, then, it's 0.0025 A sub n plus 100. Now, once again, we can solve for A sub n plus 1 by rewriting the change as the difference, right? Because it's a difference equation. So A sub n plus 1 minus A sub n is 0.0025 A sub n plus 100. And then solving for A sub n plus 1, once again, move that A sub n term over. That's one of those. So we're going to get 1.0025 A sub n plus 100. And again, A naught is 1,000. And this is our discrete dynamical model. Now, these models are nice because they're precise. There's no messiness like we might have seen in most of the other modeling questions we've done, because we're just trying to learn the basics of this idea. Now, if we want to do this after 5 years, so if we want to know 5 years, that would be 12 months. So we would need to know A60. That's the question. And if you work that out, A sub 60 is approximately $7,626. Now, one thing to notice is that we had a lower interest rate and a lower starting value, and yet we still ended up with more money in the long term. So that's the, first of all, the power of saving a little bit every month. So that makes a difference. And also that we still had some interest coming in. All right. What about an explicit formula? This one is not so obvious, so we're going to leave this as an exercise to try to figure out on your own. But I'll go ahead and give you the formula so you can compare. And the formula for this is our value here, 1.0025 to the nth power, so similar to before. But the difference is now, instead of multiplying by A naught, we multiply by A naught plus 100 over 0.0025, and then we subtract 100 over 0.0025. All right, so that's the explicit formula. Again, work that out on your own, see if you can be clear where that comes from. And let's take a look at the spreadsheet way of doing these problems now, because a spreadsheet is a great way of doing recursive relationships. So here we have our example number 2. We have it set up where we have 20 quarters, and we start with 5,000. I'm going to put an interest rate here of 0.05 divided by 4. So I'll let Excel do the work for me. And then remember, the change was basically the rate times the previous value. And then because I'm basically doing the next term, I want to add that previous value. So if you recall, it was A sub n plus 1 plus the rate times A sub n. And so we get, after 1 quarter, $62.50 of interest. Notice there's another way you could have written this. You could have written this as 1 plus this number times the previous value. If you prefer that, it's not going to change the final answer. And then I can double click the corner here to get a, to drag it down. Notice though I'm getting the same number, and that's because Excel is only assuming that I want everything to shift. I want the previous value to shift, but I want the rate to stay constant. So I need to put a $sign here in front of this 2 so that when I drag down that column, that 2 won't change. I don't need all those decimal places, so I will only leave 2 decimal places. And if we want to see what A20 is, we get $6,410 as we expected. All right. And if you don't want to scroll down, you can even do A20 equals, and then you could just come down here. And then you can see how the interest rate would change your amount. So for example, if I only got 3%, then going from 5% to 3% costs me $600. And if we could go up 7%, well, we've gained about $600 from the 5%. Likewise, we can do the same thing on our other example here. Now I'm taking 3% divided by 12. So there's the 0.0025. I'm saving $100 a month. And again, remember, it's the previous amount plus the interest rate times our previous amount plus our monthly deposit. And so we have $102.50 more than the month before, but of course 100 of that was the deposit we made out of our own money. Now, if we want to drag this down, once again, we need to have these numbers be constant. So I need a $sign in front of the 2 and a $sign in front of the 3 for I2 and I3. And now if I drag these down, and once again, 2 decimal places. And if I want to know what A60 is, I can come down here to A60. There's the 7626 like we expected. Oops, try that again. And once again, you can see how that number changes if your interest rate goes up. So if we could get that 5% again, make a few more $100. If I had started with $5,000 like I did before, we get $13,000. And notice this actually translates to the previous one. If I change this to a 0, then I'm back down to the $6,400 number. So by setting up a spreadsheet in this way, there's 2 advantages. One, it works very well with difference equations because of the recursive nature of what we're doing. And it also works very well with a model analysis because we can quickly change these numbers to see how things change. And so depending on what you're doing, that flexibility can be really handy, especially on something that you don't have, that you do have control over. The interest rate may be fixed, so you may just have to leave that at 5%. But if you're trying to decide how much to save each month, you can see how much various increments of amounts will change that number. Now, as we said, this first section has been just on the basics and very well-defined modeling situations with not really any error. In the next section, we'll see what happens when things get messier. And we'll see you there.